In this example, we want to graph this piecewise function and then determine the values of a for which the limit will exist as x approaches a. And I like this problem because it offers a great opportunity to review a little bit of your algebra skills from one of your previous classes, specifically how to graph a piecewise function. And you'll notice that piecewise functions pop up pretty regularly throughout the study of calculus. So it's a good idea to have a nice strong handle on how to work with these functions. So this piecewise function has two pieces. My first piece is basically y equals x plus 1 squared plus 1. So let's start with that piece. Y equals the quantity x plus 1 squared plus 1. So remember, this is going to be a parabola. The parent function is y equals x squared, but we have a shift. So this x plus 1 causes a shift to the left 1, and then this plus 1 is a shift up 1. And I always recommend with piecewise functions that you graph them in pencil. So switch over to a pencil if you're in pen right now, because we are going to erase part of this graph. Right now, I want to go ahead and graph the entire parabola. So if we go left 1 and up 1, then the vertex is at -1, 1. And then because this is following the shape of a basic y equals x squared parabola, we know that from the vertex we can go left 1, up 1, and right 1, up 1 to get to the next 2 points. And then from the vertex we could go left 2, and 2 squared is 4. So if we go left 2, then we're going to go up 1, 2, 3, 4. And then from the vertex, if we go right 2, we can also go up 1, 2, 3, 4 to get to my next 2 points. So this is our basic parabola. There has not been any stretch or compression, and this parabola opens up. So that's the entire parabola. However, this is a piecewise function, which means we don't want to graph the entire parabola. We only want to graph part of it. So now we move on to the next portion of the function, which is the domain statement. We only want the piece where x is less than 0. So if you go to x equals 0, at x equals 0, that's this point right here, 0, 2. And basically, we only want the values where x is less than 0. That means we are going to keep the part of the graph to the left of this point, and we're going to erase. So get out your eraser, and you're going to erase the portion of the graph that is to the right of this point, because we only want x values to be less than 0. And because that is less than, not less than or equal to, that also means we need to change this to be an open dot at x equals 0, because we don't want to include 0 on this portion of the graph. There you go. So now let's move on to the second piece. And my second piece here is, again, y equals just x. So y equals x is simply a line. And that line has a y-intercept of 0 and a slope of 1. So once again, if you wanted to graph the entire line, this would be the whole line, y equals x. However, we are going to look at that domain again. We don't want the whole line. We only want the portion where x is greater than or equal to 0. So if we go to where x equals 0, that's this coordinate here, 0, 0, and we want to keep the part of the graph where x is greater than 0. So that means we're keeping everything to the right of this point and erasing everything to the left. And then I'm going to just fix that point 0, 0, because this was x is greater than or equal to 0, that's a solid dot at the origin. So here are the two pieces of this piecewise function. So now on to the calculus part. This question is asking, determine the values of a for which the limit will exist. So if you look at what a is the value that x is approaching. So it may actually help you to first ask yourself, where will the limit not exist? And in fact, hopefully you can see that the limit is not going to exist at 0. So for example, as x approaches 0, from the left, my y values are approaching 2, but as x approaches 0 from the right, my y values approach 0. So that means that the limit as x approaches 0 of our function, which I almost wrote f of x, but this function was labeled h of x, that limit does not exist. Now that doesn't answer the question because the question wanted to know what are the values of a for which the limit will exist. So this means that the limit will exist at any value other than 0. And so I'm going to write the values of a where the limit will exist. I'm going to write it as an interval, kind of like we do with domain. So a can be any value except for 0. So therefore, a can be from negative infinity to 0, and then we'll use a parenthesis to skip over 0, and then from 0 to infinity. So this is actually the answer to this question. The values of a for which the limit will exist are all of these values here, all values except for 0.